Let's investigate critical angle. First, we need to understand some terms. Here we have a light source shining from an incident medium into a refracted medium. So we have a boundary between two media. And at that boundary, two things happen. Some of the light is reflected off the boundary back into the incident medium. And some of the light travels into the new medium, into the refracted medium. And as it does so, it is bent. It is refracted. So we call the light approaching that boundary the incident ray. That part of the incident ray that gets bounced back into the incident medium is called the reflected ray. And that part of the incident ray that passes through the boundary into the new medium and is bent in its path is called the refracted ray. To help us to speak about these various concepts, we use an imaginary line that we draw in, and we call it the normal line, and we draw it at right angles to the boundary between the two media. So here we have the incident ray, the reflected ray, and the refracted ray with the normal line intersecting them all at the boundary between the two media. And we use the normal line to help us to describe the various angles involved. The angle between the normal line and the incident ray is called the angle of incidence. The angle between the normal line and the refracted ray is called the angle of refraction. And the angle between the normal line and the reflected ray is called the angle of reflection. Now, so far we have been disregarding the reflection and focusing just on the refraction. But let's now look at how the angle of incidence and the angle of reflection compare to one another. And this is described by the law of reflection. Always the angle of incidence is equal to the angle of reflection. Another concept that's important for us to understand is the concept of refractive index, which is related to optical density. So for example, for air, the refractive index is 1. And what that means is that light travels at the same speed through air as it does through a vacuum. Whereas here we have some other kind of medium, and its refractive index is 1,6, which is a greater refractive index than air's refractive index. And what this refractive index tells us is that when light travels through this particular medium, it travels 1,6 times slower than what it does through a vacuum. And the reason for that is because this medium is optically more dense. It has a greater optical density than a vacuum does, or than air does, and therefore it's more difficult for light to travel through it. That's why it goes so much slower through it. And we have seen that when light travels from an optically less dense to an optically denser medium, it is refracted towards the normal. Whereas when it travels from an optically denser to an optically less dense medium, it's refracted away from the normal. And this is very important for understanding critical angle. Because what happens with a critical angle is that light travels from an optically denser to an optically less dense medium, and therefore is refracted away from the normal. But at critical angle, that refraction away from the normal is so great that the light is refracted at 90 degrees to the normal. In other words, it's refracted such that it travels along the boundary between the two media. And if you increase the angle of incidence a little more than critical angle, light can no longer enter the second medium and total internal reflection occurs. This can only happen when light travels from an optically denser to an optically less dense medium. Why? Because only when light travels from an optically denser to less dense medium does it get bent away from the normal, in other words, closer to the boundary between the media. So what is critical angle? It's the angle of incidence which causes an angle of refraction of 90 degrees. And beyond that angle of incidence, total internal reflection occurs. Critical angle is best understood by actually observing it. So let's see, what have I been speaking about? Let's open our simulation bending light. We can open more tools. Now I'm going to shine the light here, and you can see here at the moment light is traveling from an optically easier medium, air, into an optically more difficult medium, glass. So the light is being refracted towards the normal. So it doesn't matter what I make the angle of incidence. Let's put the angle of incidence in. So you can see at the moment it's 56,4 degrees. No matter what I change that to be, I'm never getting total internal reflection. I'm getting some reflection, but not all the light is being reflected. Most is actually traveling through into the second medium. Most is being refracted. And no matter what I do with the angle of incidence, I always get some reflection, some refraction. There's no total internal reflection. But if I change this round, let's make the receiving medium air and the incident medium glass. So now light is traveling from an optically more dense into an optically less dense medium. And notice now the light is being refracted away from the normal, closer to the boundary. And look what happens now. As I increase the angle of incidence, of course that also increases the angle of refraction. It bends the light even closer to the boundary. And then I reach a point, I'm nearly there, I'm not quite. The moment the angle of refraction is 87 degrees. If I make the angle of incidence a little more, then it's extremely difficult to get it to be 90. I probably won't get it closer than this, 89,4 degrees. So you can see that it's bent almost along the boundary between the two media, meaning that my angle of incidence, which is now 41,8 degrees, is nearly at the critical angle. It's not quite. So I increase it slightly. And as I do so, do you see? A little more, and I stop getting refraction. I now only get total internal reflection. And always with reflection, the angle of incidence equals the angle of reflection. If I increase the angle beyond that, I still only get total internal reflection. So these incident angles are not called the critical angle. It's only the minimum angle that causes total internal reflection that is the critical angle. So we get it as small as possible. So theoretically, the critical angle is the angle of incidence that causes an angle of refraction of 90 degrees. But practically, when you actually measure it, it's extremely difficult to get that exact point. So what you practically do is you make the angle small enough, as small as possible, while still getting total internal reflection. Go even smaller, and now you stop getting total internal reflection. It's partial internal reflection, and then you also get refraction. Make the angle a little bit bigger, and I'm nearly there. It's nearly at 90 degrees, and there we could probably take that as being the critical angle for these two media.